My first presentation is about the definition, diagnosis, and coping with non-proportional hazard. This is my disclosure. And clinical trials in cardiovascular disease often involve a time to event outcome. Patients are followed up from randomization until the occurrence of a cardiovascular event or the end of the study. In such trial, we use log-rank test and to compare the Kaplan-Meier survival curve, and we estimate an average and constant hazard ratio from Cox proportional hazard model. If we take a look at the same example again, we can easily see that the Kaplan-Meier curves proportionally diverge from each other over time. We can also see that the average hazard ratio against time remain constant. This is also known as proportional hazard, and the traditional time to event methods work well in this regard. But let's have a look to Excel trial. We clearly see that the Kaplan-Meier curves are crossing each other at the 20 months of follow-up. 30 months of follow-up. Just this finding, the crossing survival curve, indicates the violation of assumption of proportional hazard. In other words, we may conclude that the estimated hazard ratio is not constant against the time. And this finding suggests this is the non-proportional hazard. Although the crossing survival curves are typical for non-proportional hazard, this is not only findings indicate the presence of non-proportional hazard. Other scenarios may also be associated with non-proportional hazard. For example, the separation of survival curves in the early phase of CHARM trial or in the late phase of ASCOT trial are also indicative for presence of non-proportional hazard. The first Excel paper published in 2016, it was demonstrated that the efficacy of treatment have diminished in the late phases, which was also associated with non-proportional hazard. Well, then how to demonstrate the non-proportional hazard? How to demonstrate the presence of non-proportional hazard? Actually, for this purpose, there are formal statistical tests as well as graphic-based methods. The Gram-Chernow test is a formal test based on Schoenfeld residuals. We obtain a p-value from this test, and according to this p-value, we can decide whether there is non-proportional hazard or not. Or a basic graph method is log-log survival plot against time. The evaluation of non-proportional hazard with graphic-based methods are likely to be more informative than based on formal statistical tests. And yes, as a matter of fact, the presence of non-proportional hazard is a really nightmare for both statistician and for clinical trialists, because we unfortunately do not have a practical guide to show us how to cope, how to deal with non-proportional hazard. Sorry. Perhaps it may be wise to consider the likelihood of non-proportional hazard in the designing period before collecting data and before statistical analysis, and proceed according to this probability. And I strongly recommend this paper to all audience to read this article on this subject written by Royston. He's a famous British statistician. So let's say we start to analyze the study and we detect the non-proportional hazard. And we already know the non-proportional hazard reduce the power of survival models with traditional time to event analysis. So what shall we do now? In Tierno's famous book named Modeling Survival Data, it is recommended to ask two questions in the case of non-proportional hazard. The first question is it real, the non-proportional hazard which you determined is real or not? And the second question is, does the non-proportional hazard matter or not? For example, have we diagnosed the non-proportional hazard with formal test or with graphical based tests? Graphical based tests or graphical based methods may be preferred over formal statistical tests. Also, the minor non-proportional hazard or the minor violations of proportional hazard may be ignored, especially if we have large sample size. Let's say there is significant or major non-proportional hazard. What would be our strategy? How do we analyze? In this case, in the case of non-proportional hazard, or for example, in the case of crossing survival curve, you cannot use traditional methods such as Cox proportional hazard model. There is a bunch of methods recommended in the statistical literature in this respect, such as stratified Cox, log normal or log logistic, AFT, restricted mean survival time, weighted Cox, weighted Kaplan-Meier, weighted log rank, or semi-parametric AFTs or milestone analysis, and etc. If the non-proportional hazard is present, assigned treatment in RCTs, the stratified Cox will not be appropriate to use, or weighted Kaplan-Meier, weighted log rank, or milestone, all of them will be a descriptive statistics. And due to their unavailability for covariate adjustment, they may be subject to criticism. The most encouraged and promising method is restricted mean survival time in this regard. And in my opinion, the log normal and log logistic parametric models that assume an effect other than proportional hazard may also be the proper method of choice. The piecewise hazard seems to be suitable method, as you see in the famous Excel trial. Hazard ratio can be estimated according to pre-specified time intervals. However, this is not very much recommended, as it will cause a significant loss of power, especially in randomized clinical trial. In the presence of non-proportional hazard, the restricted mean survival time is one of the most preferred methods. Let me briefly talk about what restricted mean survival time, or RMCT, is. In fact, the area under the Kaplan-Meier survival curve is known as mean survival. If you want to calculate this area up to the pre-specified time, it will now be restricted mean survival time. If we assume we have two treatment arms, the difference between RMCTs, or a restricted mean survival time, will be an appropriate treatment effect for us. You can even plot the difference in restricted mean survival time from the zero time to the time you pre-specify it. For example, we can conclude the following from this figure. At the 6 months target vessel revascularization free survival time was 3 months longer after CABG compared with PCI. Finally, I will briefly present our algorithm or my algorithm for survival analysis in the presence of non-proportional hazard. It wouldn't be appropriate to use to those parametric survival models assume proportional hazard assumption such as Weibull parametric model or Cox proportional hazard model. However, weighted Kaplan-Meier or weighted log rank or especially restricted mean survival time or milestone analysis can be used. However, when a covariate adjustment is required, accelerated failure time, AFTs assume an effect other than proportional hazard, or some extension of Cox proportional hazard model, such as piecewise hazard ratio, stratified Cox model, or weighted Cox may be used. Or sometimes Buckley-James model as a semi-parametric AFT could be a good option in this case. And here in my last slide, you may see some reviews about non-proportional hazard published in major cardiology journals in this year. I strongly suggest reading them. Thank you very much for your attention. We can proceed to